Hello, this is Fırat Tigrek. In this Pencast, we will derive the maximum likelihood estimator for signal parameters from data with additive white Gaussian noise. The data is assumed to consist of a signal and additive white Gaussian noise. Thus, the noise samples are drawn from a Gaussian distribution with zero mean and sigma squared variance. The probability density function for noise samples is the Gaussian function. This function forms the basis of the likelihood function. Now let's work it out together. The trick is to keep in mind that the error between the data sample and the underlying signal model is the noise. So we may replace the noise samples by the error term. Now, what we obtain is the density function for the data sample, which depends on the parameter theta. We are usually interested in a sequence of data points to estimate our parameter theta. So let's consider a data vector x that consists of capital N data samples. The probability density function for a sequence of samples is the multiplication of the probability density functions for individual data samples. We may write this sequence of multiplications as you see on the screen. So, essentially, we are multiplying a set of Gaussian probability density functions. Once we feed the data samples into this equation, we obtain the likelihood function. The multiplication translates into a sum in the power term. At this point, we should consider taking the natural logarithm of the likelihood function. The natural logarithm of the multiplication of two terms is the sum of the natural logarithms of each term. This means that the natural logarithm also extracts the exponent over the base e. So here, written in blue, we see the log likelihood function, and the utility of using the log likelihood instead of likelihood is evident in this example. Now, how does the maximum likelihood estimator work? The formal description that you see tells us that the maximum likelihood estimate of the parameter theta maximizes the likelihood function. That's obvious. This also means that if we take the partial derivative of the likelihood function with respect to the parameter theta and evaluate that partial derivative at the maximum likelihood estimate theta hat, we must obtain 0. So let's take the derivative. The derivative function is distributive over addition, so we can write the derivative of the log likelihood function as you see on the screen. The second term on the right-hand side does not depend on theta, so the derivative with respect to theta is equal to 0. By chain rule, we take the derivative of the squared term. All we have to do is to set this equation equal to 0 and solve for theta. Easier said than done. We cannot go further without specifying the signal model. So let's move on. How about a linear signal model? A linear signal model consists of an observation matrix, capital H, multiplied by the parameter vector theta. So let's switch to matrix algebra. The first step is to write the squared error term that pops out of the log likelihood function in vector form. This move should be familiar from the least squares estimator. So the log likelihood function is rewritten in terms of vectors. We proceed by taking the derivative with respect to the parameter theta, which can also be a vector. The first term on the right-hand side is eliminated again, just as before. Now, we need to take the derivative of this matrix algebraic expression. Fortunately, it's not that hard. Let's first open up the vector multiplication to see how the partial derivative operates on each term. The partial derivative of the x transpose x term with respect to theta is 0. So let's get rid of that. The derivative of the remaining terms are as shown. Now, all we need to do is to set this equation equal to 0. Note that this is exactly the same expression as the least squares estimate. So, for data in additive white Gaussian noise, the least squares estimate is equivalent to the maximum likelihood estimate. This pencast concerns the white Gaussian noise. If you consider colored noise, how do you think the estimator would change? Please give it a try. Start from the Gaussian probability density function with a covariance matrix instead of the variance term for the white Gaussian noise, and follow the same derivation steps. If you have any questions about this pencast, please contact us. Have a nice day.